This is the first of two lectures for Chapter 6. In Chapter 6, we will be looking at solutions and colloids. Let's first look at solutions and define a solution. A solution is made up of two components that are mixed together. Here we're showing a solid mixed in a liquid to form a solution. That's one example of a solution, that is a solid that's mixed in a liquid. So let us get some terms defined before we actually go into our detailed discussion. Solvent. A solvent is that fraction of a solution in which the other component is dissolved. So solvent, let us imagine first of all you went in the kitchen and you mixed sugar and water. So the solvent here would be water because the sugar is dissolved in that solvent. The solute is a substance that's dissolved in the solvent. So think about this carefully. The solute would represent now the sugar that's dissolved in the solvent. So pay special attention to these terms because we will be using these terms throughout this chapter. Solvent and solute. We mentioned earlier that you can mix a solid in a liquid and that would be a solution. But it's possible to mix a gas in a liquid, and of course as we know, that's carbonated water. Another example is, of course, air. Air is made up of gas in a gas, and of course the appearance is a gaseous. One that's we're familiar with is 14 karat gold. It's a mixture of a solid in a solid. So it's gold that's actually mixed with silver and sometimes iron to get a mixture of 14 karat gold. So again, you should be able to determine what is a solution and the components of a solution: solvent and solute. Let us look at some characteristics of solutions. The main connection here that we have done before is that solutions are homogeneous. So all of the characteristics that we looked at when we looked at homogeneous solution apply here. So let's go through them one by one. It's uniform. In other words, you look at a solution of salt and water mixed together, it's a uniform solution. They do not separate on standing. So in other words, if you take a mixture of salt and water and have it sit around for days, it's still that uniform solution. It does not separate into components by filtration. You may remember we discussed an experiment the last time where we had salt and iron, and we could dissolve the salt and filter off the iron because that's not a uniform solution. Again, here the solvent and solute can be mixed in any combination. Again, imagine mixing sugar and water. You can mix 10 grams of sugar in 100 mils of water, or you can mix 0.5 grams and see. And we mentioned earlier that they are homogeneous. It's uniform throughout, and solutions can be separated into pure components by physical means. In other words, if you have again a solution of salt and water, you can separate them into salt and water by, of course, as you know, boiling off the water and condensing it. And of course, what's left behind would be the salt. So that's one way of separating out the components of a solution. Solubility. Solubility here is a physical property of a solute. So in a particular solvent, there is a maximum amount of solute that can be dissolved in that solvent. So again, imagine salt and water. There's a maximum amount of salt that can be dissolved in a specific amount of water at a given temperature. Of course, as you can imagine, it's very soluble. So we described solubility of solutes as very soluble or not as soluble. Some are even described as insoluble because they're not soluble in a particular solvent. This just gives you an idea of the solubility of different compounds. It's typically expressed as grams in 100 grams of solvent, here water. Some other terms for solubility. Sometimes we have a saturated solution. So a saturated solution is one that has the maximum amount of solute in that solvent at a given temperature. Keyword here is at a given temperature. Again, getting back to salt and water, or sugar and water. As you know, at a particular temperature, you can dissolve a specific amount of sugar. If you should increase the temperature, you can dissolve more. So at a specific temperature, what's reported is that amount that can be dissolved, and that's called the saturated solution. An unsaturated solution is a solution that contains less than the maximum amount. And of course, a supersaturated solution contains more, a lot more than the maximum amount. And typically when these solutions are disturbed, this excess solute here falls out of solution and it's precipitated at the bottom of the solution. Let us look now at the solubility depends on several factors. One aspect that we need to look at here is the polarity of the solvent and the solute. Okay, so what's described here is like dissolves like. Let's see what that means. If we have a polar solvent, it will dissolve a polar solute. So just imagine here water, which is polar. Of course, as you know, it's H2O. It has polar bonds and the entire molecule is described as polar. It will dissolve sodium chloride because sodium chloride is an ionic molecule which has Na plus and Cl minus. So that's why it's described as like dissolves like. A polar solvent will dissolve a polar molecule. It goes the other way. A non-polar solvent, such as benzene. Benzene is a non-polar molecule. It contains only carbon and hydrogens. It will dissolve a non-polar molecule such as carbon tetrachloride, which is non-polar. Okay, even though it has polar covalent bonds, but the overall polarity of carbon tetrachloride is non-polar. So therefore, a non-polar solvent will dissolve a non-polar solute. So that's why this term applies. In general, like dissolves like. As you can see here, here's a classic example. Diethyl ether, which is non-polar. If you mix that with water, which is polar, they will not dissolve in each other. We call this a heterogeneous mixture. So they separate out into layers here because this is non-polar and this is polar. So again, you should be able to tell what solvent will dissolve a particular solute based on the polarity of the solvent and the polarity of the solute. Temperature. It's not surprising that temperature is related to the solubility. Again, taking our classic example, mixing sugar and water. As you know, if you take ice water and try to mix a lot of sugar into it, it does not dissolve. But if you take hot water and dissolve sugar, it dissolves much easier. So as you can see here, as the temperature increases, the solubility of a solute, such as a solid, dissolves in a liquid solvent. On the other hand, however, gases, it's the opposite. As the temperature increases, the solubility of a gas in a liquid decreases. Okay, so as this temperature increases, of course, just think of your soda pop. If you should open a can of soda and increase the temperature, all the carbon dioxide will be escaped or coming from it. It will be dissolving much less carbon dioxide at a higher temperature. Pressure. Little effect on liquids or solid solutions, but as you can imagine, for solutions that contain a gas such as carbon dioxide, it has an effect. So the higher the pressure, it increases the solubility. So as the pressure increases, the solubility of a gas increases in solution. As you can imagine, again, you have your soda, and if the pressure is increased, more carbon dioxide will be dissolved compared to a lower pressure. Here is an important aspect of this chapter. That is the concentration. So you will need your calculators from here on. So you may want to pause the video at this point and get your calculators. And make sure you have it all charged up and ready to go, because we will be doing some calculations. The typical concentration that we will see in this chapter is weight of solute per volume of solution. That's W over volume. And that's described as weight percentage. So for example, 10 grams of table sugar dissolved in enough water to make 100 mils is described as a 10% weight volume. Notice the key here is weight volume, because we use 10 grams in a specific volume of solution. We'll use that more than the other two here. The other two here is weight and weight. So the weight of the solute in the weight of the solution is described as the weight percentage. And of course, as you can imagine, the volume, so a specific volume of solute in a specific volume of solution is described as the percent volume. But we'll place more emphasis on weight volume. Okay, let's see how this is done. So if you're asked to make a solution, and by the way, for some of you guys who are in the medical profession, you oftentimes see the medicine is delivered as a solution, and typically it's weight volume. So here's how it's typically done. We have here a solute, here it's a solid, and here is our solvent, in this case water. So you add this to a volumetric flask, then you add water to it to dissolve it, shake it up, and then you fine-tune the concentration to make sure you have an exact volume. The key here is an exact volume. So if this volumetric flask here is a 250 milliliter, you make it up to exactly 250, and that will give you the exact concentration of solution that was made. Let us apply that concept. So carefully, let's look at this problem. Get your calculators. So here's an example. A 250 milliliter bottle of vinegar contains 5% acetic acid. Of course, as you know, vinegar is really acetic acid in water. So in this case, just imagine here you have here a 240 milliliter bottle of vinegar, and it's labeled as 5%. The question is, how many grams of that solute is present? Here the solute is acetic acid. Conversion factor is right here. Weight, volume, percent is equal to the mass of solute over 100 milliliter of solution. Notice solution. So you just set this up. You have 5 grams. That's 5 grams in 100 mils is 5%. So once again, 5 grams in 100 mils is a 5% acetic acid, but we have 240 milliliters. So here it is. The solutions cancel, and you end up with 12 grams of acetic acid. Conclusion: a 240 milliliter bottle of vinegar that's labeled as 5% acetic acid contains 12 grams of acetic acid. Let's turn that around slightly. What is the concentration of 240 mils of vinegar that contains 12 grams of acetic acid? So let me say it again. So what is the concentration in weight volume, specific concentration here, of 240 milliliters of vinegar that contains 12 grams of acetic acid? This time we have 12 grams in 240 milliliters. Notice milliliters. So if this were given in liters, you have to convert it to milliliters. So this is 240 milliliters, and of course percentage because it's weight volume percent. So this would be 5%. So again, so you should be able to convert mass into percentage, and if given the percentage, determine the mass of solute that's in a solution. As chemists, the unit that we typically use is called molarity. So pay special attention to that word, molarity. As you can imagine, it has to do with moles. So by definition, molarity is in moles of solute per liter. Notice this time it's per liter, not milliliters. Liter of solution. So here is the equation or conversion factor that you will be using to do the calculations. So the molarity, typically written as large M. So whenever you have large M, that means molarity, or a unit of concentration in chemistry. The definition is moles of solute divided by liter, or liters of solution. So let's see if we can apply that concept. How many moles of NaOH are in 2 liters? Notice here 2 liters. So liters is given of 0.15 molarity. Notice again, this is big M, so that means molarity. Using this equation here, right here, we just substitute the knowns and calculate the unknown. So molarity is 0.15 big M. Number of moles we do not know, and that's what we're trying to calculate. The volume is 2 liters. Make sure it's liters and not milliliters, because this is by definition. So 2 liters, doing the calculations, you end up with 0.3 moles. Conclusion: there are 0.3 moles of sodium hydroxide in 2 liters of 0.15 molarity NaOH. So think that one through. As a matter of fact, you may want to pause the video and just think this one through until you understand that concept. Let us look at another example here. How many grams? This time it's how many grams. So careful. How many grams this time, not moles, of NaOH are in 2 liters of 0.15 molarity? How many grams? What we did previously, we calculated the moles. So we have to convert this molarity here into moles. So this contains 0.3 moles in this concentration. Once you have the moles, you can convert moles into grams using this conversion factor. And of course, this is one you are familiar with from last chapter. 1 mole of anything is equal to the molecular weight of anything in grams. In this case, 1 mole of NaOH is equal to the molecular weight of NaOH in grams. So you'll have to get your periodic table and your calculator and determine the molecular weight of NaOH and use this equation here to calculate the number of grams. This is the molecular weight of sodium hydroxide. That will be 1 mole. They cancel out, and of course you end up with 12 grams of NaOH. Conclusion: there are 12 grams of NaOH in 2 liters of 0.15 molarity solution of NaOH. Lastly, let us look at another example. If the concentration of NaCl in blood serum is approximately 0.14, so again, notice 0.14 big M, which means 0.14 molarity. What volume contains in 2 grams of NaCl? Notice again, here's grams. So more than likely, you're going to have to convert grams to moles. Remember, as chemists, we deal with moles rather than in grams. So let's convert 2 grams of NaCl to moles. Here is the conversion factor, which you've seen before. Applying it, we get 0.034 moles of NaCl. So we have 0.34 moles of NaCl in that solution that we're looking at. Next, we need to find the volume in liters that are contained in this many moles. Here is the equation. Molarity is equal to moles divided by volume in liters. We know the moles. Here are the moles. Here it is right here. We know the molarity because here it is right here. That's the molarity. And the only unknown is the volume. And notice it's in liters. So once you set this up and calculate for the volume, you will end up with 0.24 liters. Okay, or you can convert that to milliliters, and that's 240 milliliters. So once again, you should be able to utilize that conversion factor of molarity is equal to number of moles divided by volume in liters to calculate either the number of moles or the volume of a solution or the molarity of a solution. Let us look at dilution. Especially again for folks in the medical field. A lot of times you get solution purchased from the pharmaceutical company, and that's in a very concentrated solution. And then when you have to work with it for the patients, you have to dilute it to give the patients a much diluted solution. So here's what's typically done. Here's your stock solution that you purchased from your company, very concentrated. You add some to a flask, a volumetric flask here, and that has to be a specific amount. And then your solvent, typically water, is added to dissolve that solution. And of course, the final is to get the final volume of that solution. So once again, let's review this. So you get your stock solution, you add it to a volumetric flask, and you dilute it to a specific volume to get another concentration of a diluted solution. Okay, let's see if we can apply that concept mathematically. So here is the equation that we will use. M times V is equal to M times V. We have 1, 1, 2, 2, which means here this could be the concentrated solution, and this would be the solution after it's diluted. So once again, concentrated solution, or the stock solution, and this would be the solution after it's diluted, which means the molarity and the volume, and the molarity and the volume. So let's apply that equation to solving your problem. So how would you prepare 200 mils of 3.5 molarity solution aqueous acetic acid if you had a stock solution of 6 molar? So once again, this stock solution here is 6 molar, which means that is very concentrated. Remember, the higher the number, the more concentrated is the solution. So we purchased from some company a stock solution which is 6 molar, very concentrated. But you cannot administer or utilize 6 molar solution. You need a much diluted solution here of 3.5 molarity. And specifically, you need 200 mils. How do you do that? So what we'll do is to put this information into this equation. So if this is our diluted solution, it would be 200 mils times 3.5. So 200 milliliters times 3.5 molarity. Again, you may want to bring this to liters. Always bring to liters, because by definition, molarity is moles per liter. So these two numbers here will go on this side, and 6 molar will go over here, and the volume we do not know. So you set that up, and you solve for the volume. And once you solve for the volume, you'll get 0.12 liters. Let me do it again, because I just noticed that they switched it here. So in this case here, you'd have 200 milliliters and 3.5 molarity you're trying to prepare. So what they're doing here is they put it on this side, M2. And the concentrated solution is 6 molar, and the volume you do not know, so here's the volume you do not know. So you solve that equation for V1. So set that up, and after you set that up, you'll see that the answer is 0.12 liters. So to prepare this solution, you will place 120 milliliters or 0.12 liters of our stock solution, 6 molar, in 200 milliliters volumetric flask, and make up that volume and do the dilution with water. And that's how you prepare that. So bottom line is, you should be able to, let me clear this, you should be able to utilize this equation here to determine a volume after dilution, a molarity after the dilution. And of course, typically what's given would be 3 variables, and you just need to calculate one unknown. Okay, before we conclude, let us just look at some other definitions here. Of course, you've heard of parts per million in concentration. What that means is basically 1 milligram in 1 million milligrams of water or solvent. And of course, as you can imagine, that's very dilute. So typically for very dilute solution, it's mentioned in ppms. Even more dilute solutions are mentioned in ppb, parts per billion. So if you look at the water quality that's coming into the faucet, and the state or the city typically provides the stats on the water in terms of lead and so on, you'll see that these are the units that are actually used because it should be very, very diluted. Okay, let us look at water as a solvent. As you can imagine, water is a solvent, and it's used routinely in chemistry and in biology and just about all aspects of science because it's such a good solvent. Let us see why it is such a good solvent. Let's take a solute, KCl. This is ionic, K plus and Cl minus. Mix it in water. What will happen is we'll get K plus as the ion. It's a plus, so therefore it's a cation, and we'll get Cl minus. It's negative, so it's called an anion. This AQ here means that there are water molecules around this ion. Here's an interesting aspect. If you should put an electrode or 2 electrodes into a solution of KCl and connect it to a battery and a bulb, it will light. There will be a light because of the charges here that move between both electrodes here. So we have a circuit of current going through, and that's what's caused the light to be shown here. So, as we have described here, ions dissolved in water, they can migrate in a solution. As we can see here, put electrodes in, the cations will migrate, and put another electrode in, the negative electrode called the cathode, the positive, the ions will migrate to these electrodes and create a circuit of electricity. A term for you, electrolyte, is a substance that conducts electricity. So KCl is an electrolyte. Depending on how bright that light is, if it's very bright, the electrolyte is described as a strong electrolyte because it conducts electricity really well. If the light is not as bright, it's described as a weak electrolyte. So again, just some terms that you should be familiar with. And that is, electrolyte is a substance or solute that conducts electricity in water. strong electrolyte is one that does a really good job, and a weak electrolyte is one that does not do as good a job. Water as a solvent, as we have described before, water is a polar solvent, and of course if we have ions such as a negative ion, it will surround that negative ion. If we have a positive ion, because it's polar, it will surround that positive ion. There are typically around 2 to 6 water molecules around each ion. We call that the water of hydration. So the AQ that you see in these equations or these reactions is really the water of hydration that surrounds these cations and anions. And here is a classic example of that. So we have here the anion, negative charge. Water is polar. This is partial positive, as we have described before. The oxygen is partial negative because it is more electronegative. And of course, as you can imagine, a negative and a positive will attract each other. Here's the other example. A cation, for example, water is polar, so this is partially negative, and this is partially positive. So the negative and the positive will attract each other, and that's called the solvation of the ions. So that's the end of this portion of the lecture for this chapter. So continue reading up on this chapter and work the problems, as many as you can, and make sure you have your calculators when you do this, because we will be asking you to manipulate these various conversion factors to calculate unknowns. So the quiz on Thursday will cover this lecture, and I'll try to get another lecture out on this chapter before the week is out, which would more than likely be after the quiz. So continue studying hard and get ready for the quiz, which will be on Thursday. Okay? Bye.